So all right, so let's get started. Glad to see all of you have made it back from, everyone made it back from spring break. Well, everyone here made it back. I see not everyone seems to has returned. So hopefully you all turned in your intermediate. You all turned in your intermediate progress reports on your project. I will start reading through those, and I'll try and give some feedback when I can. So hopefully in the next week or two. So homework 3, I've heard is almost done being graded, and the scores will be out soon. And then the quiz, which we had last week, is also pretty much all graded. So I expect to have those up maybe on Wednesday or so. But by Wednesday, there's just a little bit left. All right. So the other thing is homework 4 is due on Wednesday. So how many people have started homework 4? How many people have not started it yet? Okay. So this one, those of you who've looked at it, it's good. It should not be as long and shouldn't take as long as the other ones. Has anyone completely finished it yet? Yeah. So this one took a lot less time, maybe. Yeah. Okay. Good. So I hope from here out the homeworks won't be as time consuming as the first half of the class. So you can focus more on the stuff with the project. Yeah, so hopefully it'll be, so hopefully that'll be a little bit better. Yeah, so hopefully everyone will be able to finish that by Wednesday, though. So okay. So all right, so then what we're going to talk about in class today is we're on the session on regression, and generally this has meant just kind of, you're kind of taking in, this is taking in 2 inputs. You have some form of measurement, and then you have some, or I shouldn't say data, and then you have some ways that you're measuring data, and then you have some observations which correspond with these measurements. And you're trying to reconstruct a model that's somehow relating these 2 things. And so we talked a little bit about some basic things in 2D, and this included these like linear regression. And we talked about how if you're doing if you're doing the least squares version of this, then there's a simple closed form solution that's very general. It generalizes to higher dimensions to these polynomial fits, and the closed form in that you can't possibly do any better than this if your goal is if your goal is to minimize the sum of the squared errors of these residuals. But there are a couple of things that that this was not good for. If you had outliers, this didn't work as well. And these were when these residuals that you're predicting, if this is your model and this is your data, and this was minimizing the errors in this direction. So you want to minimize the sum of these squared distances from your data, which are these blue points, to this model, which is this line. You want to minimize the sum of these squared distances. If instead you want to minimize the sum, say, of the square root of the distances of this projection onto the line, these distances are closer, then you do stuff based on you do stuff based on PCA, right? And so we talked about that as well. And this generalizes nicely to higher dimensions. And it's also, there's a simple procedure you can call inside MATLAB using the SVD to give you the, that essentially can be translated into the solution for PCA. This was also minimizing the sum of squares and still had potentially some problems with outliers. So in the lecture on Wednesday, we'll talk about doing some ways of regularizing this, where you add some bias into the solution. And if you add bias, it turns out you can do slightly better. And it's a slightly better version of doing this least squares. This was only the best if your solution had to be unbiased. If you add bias in here, we'll see how you can do slightly better. The other thing with PCA that it was useful for is that if you went from if you had data in a very high dimensional space, so if you're in a very high dimensions, so say you have data and that each data point has lots of attributes to it, and you want to map this down to some low dimensional space. So you say, I want a few number of attributes that could be maybe combinations of these attributes that represents the data. Then you could also use PCA for doing this. Okay. This had the problem in that it was slow if your data is really big. It required doing this SVD, which is fairly slow on really large data sets. We talked about approximate versions. We also talked about, so we had a guest lecture for my student Mina in the last lecture. And one thing she talked about is you can actually choose some specific subset of the data points to represent this instead of getting a linear combination of these into these low dimensions. And that can give you more representation. Okay, so this section here is on, this is often called dimensionality reduction. Okay, and so the goal of this lecture is going to be two things. The first one is going to be this Johnson-Lindenstrass form, which is a randomized approach to doing dimensionality reduction. There are kind of two main ways of doing dimensionality reduction. One is using PCA, and the other is using this Johnson-Lindenstrass transform. And so in most cases, doing PCA is better, but there's some cases where doing this is better, and so we'll talk about this and explain what's going on here. But it's really a pretty simple process. The other thing we're going to do in this lecture is we're going to talk about the compressed the compressed sensing problem. Okay, and so what compressed sensing is doing is it's making a different kind of assumption about the model. Before, with linear regression or with these other forms of, most other forms of this dimensionality reduction, you're assuming usually that there's some linear model that fits this. You could do this polynomial version of linear regression, but it kind of goes through this intermediate form that's also linear, right? So if you're doing compressed sensing, so there you're saying to simplify the model, I'm going to assume that's linear to fit the data. In compressed sensing, you're making a completely different sort of assumption. Not that it's near linear or something like that, but that the model is sparse. So it's assume, should be 1L, okay, fix that, is that the model is very sparse. That means that when doing this, kind of coming up with this way of kind of figuring out how to represent these very complex data set in a simpler way, you're assuming that there are only a small number of parameters which are describing this. And so you can again think of these as dimensions, and you're saying there are only a few number of dimensions which actually are somehow affecting my data. And so it's trying to pick out these dimensions. And so there's a whole literature. It's a huge literature. This whole idea of doing compressed sensing is probably only like really largely only maybe 10 to 15 years old. So but there are hundreds of thousands of papers on this now. But we're going to talk about the simplest way of doing this. That's called orthogonal matching pursuit. Now, and I'll allude to some of the more advanced ways of doing it as well, not just this lecture, but the one on Wednesday as well. But this orthogonal matching pursuit is going to be absolute simplest way, and if your data is kind of a really easy problem, then this way is still going to work. For really hard problems where it's harder to find the best sparse solution, then there are going to be other techniques which will work better on those problems. But on easy ones, this one is going to work just fine. And it's a lot simpler to understand what's going on. Okay, so these two topics are not totally related to each other, but we'll just go through this one quickly. I think it's important to kind of know this, because if you're ever looking at papers on this, you'll say, what's this? What are these Johnson-Lindström random projections doing? So I'll explain that. Okay, so let's talk about this. So the Johnson Lindenstrass. Okay. Lindenstrass. And these are called random projections. Okay. And so this was based on, these are two people, Johnson and Lindenstrass, and I think it was in '85 they had that paper, and this result was kind of some small lemma in this much larger paper on some variety of topics. And so this is sometimes referred to as the Johnson-Lindström lemma. So a lemma is like a smaller version of a theorem. So they didn't even think this was that important at the time, but this is kind of the most important thing that kind of has come out of this work. Okay, so the goal is that you start out with some point set. So this is a point set that lives in some d-dimensional space. And so we're going to think that d is very large here. And so the beauty of this is that it's not going to matter how large d is, how this is going to work. And so what your goal is going to be some mapping that goes from Rd to Rk. And so in this mapping, we can say that when you apply this to a point set, you're going to get another point set Q. So every point in here, Pi, is going to map to some point Qi in here. Okay? And so the goal is going to be such that you're going to look at the distance. So look at for all points Pi and Pj in our point set, we want to look at the distance between Pi and Pj, and we want this to be similar to the distance between Qi and Qj. Okay, so you want it to be less, and in fact, you want that if I shrink it by a little bit here, so I'm going to say 1 minus epsilon. So we're going to say this is going to have, epsilon is going to be something small, between 0 and 1. So you can think of like epsilon equals 0.01 here. So some small quantity. So if I shrink it by 1%, then it's always going to be less. Then the true distance will always be less than my new distance. And if I look at, and I want it to be larger than if I increased it by 1%. Right? So if I increase, this part here is increasing by 1%, and this is decreasing. So I want for all of my points in this new k-dimensional space to be approximately the same. So all my new points to be approximately the same as the old points. Okay, so I want all the distances to be about the same as they were before. But I want the dimensionality to be much smaller. Okay, so this is a much stronger kind of sort of guarantee than we got when we were dealing with PCA. We're dealing with PCA, or we're dealing with that result of the SVD, right? What we got was that if you looked at the differences between the point and its new location, right? Before we're mapping every point onto a smaller dimensional space, and that mapping, that distance of that mapping was small, and it was all of them were small on average. Before, so with PCA, we were somehow looking at a quantity that looked like pi minus qi squared. And we wanted to make this small. We want to make it, so that means the distances are small on average. So now here we're in RK, but we think this is a subspace of RD. Right, in order to make this make sense. So this was saying on average, these distances were small, right? So this is what PCA was doing. So with the Johnson-Lindenstrass random projection, you want to get this property, okay? So, and it turns out that we're not going to be able to, it's going to be a randomized algorithm, so we're going to have this epsilon term, and we're going to say this is true for all points with probability at least 1 minus delta for some another parameter delta, and delta will again be something small, some small value. So you want to say, so with 99% probability, all distances are preserved within 1%. So this is the sort of guarantee we want. So this seems much stronger than before. So with PCA, we could get down to like 2 or maybe 10 dimensions, and you could get some, and you'll see in your homework that the homework 5 that this will work, often work pretty well with just a few number of dimensions. With the Johnson-Lindenstrass approach, using 2 or 10 dimensions is not going to work that well. So in order to get this to work, we need to use k equals to roughly 1 over epsilon squared. Let me write this bigger so it's clear here. 1 over epsilon squared times log of n over delta. Okay, we're going to get this bound on the size of the subspace. So that's the k that's right here. So we're going to go down to a smaller dimensional subspace, but we're going to need this many dimensions to get this guarantee to work. So actually what's in here, this is only proved kind of in the limit. There's some constants inside of here that I've skipped, that I haven't written down, but they're probably something like between 1 and 2, so it's not such a big deal. Yeah?
Is that the number of points?
No, this has, so n is the number of points. Okay. So n equals the size of p. Yeah, great, thanks. Yeah, so it has to do with the number of points. It does not have to do with d. So d can be as large as you want, and you still only need this many dimensions. Okay, so there's sometimes there are some bounds that you want to use where the d term shows up inside of here, but it's always larger than the original dimension. But there's some strange cases where you actually still want to do this. If you're doing like approximating of matrices, there's an approach that, like the matrix sketching approach that Mina talked about last week, there's actually an approach based on this. We actually want this term to depend on d. And it still makes sense to do that for weird reasons. But in most cases, the cool thing is that this is independent of the dimension. And it only depends based on a log of the number of points. Okay. So in general, though, this only kind of, it's really only pretty useful when it's kind of as a rule of thumb, or rule of thumb. I would only, the people have done various studies, I would only use this when d is greater or equal to something like 1 million. And k, your desired dimension, is something like at least 200 for this to actually be that useful. And maybe you want to actually put this at like 500. Okay, so if your goal is to do something where you can then, with PCA, you can go down to 2 dimensions and you can kind of plot the data points. For this is not going to work that well. If you do have 1 million of these dimensions and you're trying to get down to 2 or 500, then maybe you get down here and then maybe it's small enough that you can run PCA exactly. So maybe that's one reason why you would do it. Or you'd run some other algorithm. Maybe there's ways people use this where they have a lot of these dimensions and they're mapping them down. So then they'll pipe this into some sort of machine learning algorithm, and then the machine learning algorithm runs faster because they only have 500 dimensions instead of 1 million dimensions. Okay. So this happens when you have data points, and the data points have lots and lots of these attributes. And you want to kind of combine them together in some way. Okay, so what are some other reasons why you'd want to use this instead of PCA? Okay, so does anyone have any idea why you'd want to use this instead of doing PCA, just by looking at what I've told you? Yeah?
Well, 2 things. First off, you're bounding individual points by error, which is kind of interesting, whereas PCA, you're bounding the sum of the points. So maybe you want to do that in certain situations. And the other one is it's a lot faster.
Yeah, right. So let's see if this works. Got to turn on the camera today. Okay. I guess that's not going to work. Okay. Yeah. So one is you're getting this stronger error guarantee, right? So if you want to do something like nearest neighbor searching, right? If you want to find these similarity searching, PCA is not going to have any guarantees. It's doing this on average. So if you want to do nearest neighbor search, so if you're doing this on average, you could completely distort some of these distances. So doing similarity search doing PCA could do very poorly. So actually, if you remember the locality sensitive hashing we talked about, it's going to do something very similar to this in the heart. It's kind of doing something like this in terms of LSH. The other thing is doing this can be much faster, right? So if you could do this down to, say, 500 dimensions and then run PCA, because this you can do in basically k times the size of the data. So I'll describe how to do this on the next slide. But you can do it in the dimension you go down to times the time it takes to read the data. Whereas PCA, it took the time it took to read the data times d again. Right? If n was bigger than d, then it would be n. This was n times d squared. And with Johnson-Liljestrauss, the time here is going to be n times d times k. So if k is much smaller than d, then this time can be is a big enough difference in order to do. So there's some other interesting things I want to point out, some differences. If you go back here, if I was doing PCA, I was mapping every data point onto this line, right, to the closest spot here. So there's some very big danger with PCA, is that if your coordinates, if your data points, they have all these attributes, but they're measuring completely different things, so the units are not the same, PCA doesn't know that, and it kind of says just which values are larger, those are the ones it preserves. So PCA ignores units. So it kind of treats all the units of all of your dimensions as being the same. So if you're doing this like with, if each data point is like a stock price, so they're all dollars, then this is fine. If they're all temperatures, this is fine. So you look at the temperatures for the past 100 days. and you want to reduce that down to, say, 10 days. Each data point is 100 temperatures. That's fine. But if you're doing something where the attributes are something like the age, the weight, and the height, then if I measured height in inches or in feet, the data doesn't change, but the results of PCA are different. So don't do PCA if you have these different attributes. Now, if you look at this guarantee, this is preserving all distances well. And it turns out that means that it preserves each of the coordinates well, too. So doing this Johnson-Liljestrauss transform, it's okay if your coordinates are different. If the units are different, it's still okay to use. It's still safe to use in that case. Whereas with PCA, that's not safe to use. Okay. The other thing that's going to happen, and I'll describe the algorithm next, the other advantage you're going to get, which is going to be important, is that this is going to be agnostic to the data. So the algorithm of doing this projection from D dimensions down to K dimensions is not going to care about the shape of the data or how the data is distributed or anything about it. So it means to describe this projection, this mapping, you don't need to see the data first. Whereas with PCA, it needs to look at the data very carefully and as part of this process. So this is going to be agnostic to data, and this will have certain advantages that you can do it to two data sets independently and then join them together later, and all this is going to work out. Okay. Okay, so how do we actually do these JL random projections? Okay, so it turns out that we're going to, so it's going to be random. So the idea is we're going to have this data set, which might be in some high dimensional space, and we're going to choose some random vector. So if this is my coordinate axes, this is a random vector u, then I'm just going to project, I'm going to pick this random vector, and then I'm going to project each of these data points onto here. And so this was doing it like PCA is projecting it, but instead of picking PCA had this way of picking the best possible direction, and that best depended on the variance of all the directions of the data. Now I'm going to pick this u at random. So I'm going to pick a direction u at random. Okay, so what does it mean to pick a direction u at random? What does that even mean? Question is already interesting in 2D, right? What would it mean to pick a direction at random?
You pick a point on the circle?
Yeah, so it turns out you want to pick a point on the circle. Right, so you can think of a unit circle, and then you pick a random point. And high dimensions, this is going to be a random sphere, right? So it's going to be a d-1 dimensional sphere in d-dimensional space. You would pick a random point on the sphere, and so this is the right thing to do. But then the question is, how do you pick a random point on a circle? Well, we talked about this before, right?
You pick a random point inside the unit sphere, and then you just say, draw the vector, and we'll divide it by its length. Okay, so it turns out picking a point inside of a random ball is harder than picking a point on a random sphere. So we want to choose u at random from all x in Rd such that the norm of x equals 1.
Okay, so what we're going to do is we're going to pick a random vector that's going to be equally distributed in every direction, and then we're going to normalize it. So that part is right, but we're not going to restrict that inside of a random ball. That turns out that's hard to do. If you picked it inside of a random square and then you normalized it, you're going to tend to get too many points in the corners. And in higher dimensions, this is going to be even worse of a problem. But what we could do, remember, is there was this, we could pick a random point from the normal distribution, right? So, and the way to do this was through this box Muller transform. And so this took in 2 points that were each that were uniform in 0, 1, and I do these. I took in 2 of these points, and the output is going to be 2 points, say G1 and G2, which are both going to be these points from drawn randomly from the normal distribution. And it turns out the nice thing about the normal distribution, if you draw, so this in 1 dimension, this was this Gaussian distribution centered at 0. But the nice thing about this is if you can define this Gaussian distribution in higher dimensions, and it's perfectly symmetric. Okay, so if I look at the isolevels around 0, it goes out. The isolevels are perfect circles around here, which means that in order to pick a point that's equally direction, if it's from a 2-dimensional Gaussian, if I have a point here, which is G1, G2, and I normalized it, then it has to lie in a ball, and it's equally likely to be in every direction. Okay, so in order to create a direction U, I take G1, G2 up to GD, which is going to be D normal of these random variables, and then I want to normalize this, and so I make it so the length is 1. Okay, and so this gives me a perfectly this gives me a direction which is a random one on this circle. So it's this random direction. Okay. So now, how do I get a coordinate of each of these points? Well, this one direction U is going to give me 1 coordinate. So I'm going to call this UJ. And so I'm going to say that a data point, P, J, I want to map to coordinate J, QJ, and I do the dot product of U with PJ, with this whole data point here. So I take the whole data point, and I take the dot product with this data point, and this gives me the jth coordinate. Right? So if I look at this data point here, let's call this point P, and this is direction U, then actually the dot product, exactly what it tells me is this distance from the origin here. The length of this projection from the origin is exactly the jth coordinate. Actually, it turns out if I do this, it's always going to be too small. So I need to do I need to do this value times square root n over square root k. Otherwise, if you're projecting to a lower dimensional space, things only get smaller. So to make it so that it's the right value, I need to kind of expand it back up a bit. Okay, it turns out this is the right way to normalize it. Okay, so in order to create this random projection, for each coordinate of the points in the new space, for the jth coordinate, I create a random direction, uj, and I take the dot product with the point, and I expand it a little bit. This is the jth coordinate, and I do this k times. And so I do this k times, and I get the k coordinates of all the data points. Okay, so by defining these vectors u1 through uk ahead of time, then I've defined the algorithm. I've defined this full random projection ahead of time without looking at the data. Just choosing these was this random process based on these Gaussian random variables, and by choosing these, then I choose these ahead of time, and then I do the dot product with all my data points. Each dot product I can do basically as fast as reading the data point, and that gives me one coordinate. Because there are k coordinates, it's k times the cost of reading the data point. Okay, so it's a fairly simple algorithm, but you need a lot of these random processes to make this actually work. Okay, there's one simpler way you can do this that people use in practice. Instead of using these GIs, each of these can be from a normal distribution, which is the simplest way, but you can also have each of the GIs coming from the set -1, 0, and +1. Turns out if you just have it randomly -1, 0, or +1, then this also works. So doing this is going to be even faster than doing the dot product. If it's a 0, I can ignore it for one of the coordinates. If it's a minus, I'm subtracting the value of that point. And if it's a +1, I'm adding it. So this operation you can do faster because you're not doing an extra dot product operation. You're just adding or subtracting it to this in order to get these coordinates. You're adding or subtracting up the individual coordinates here. So it turns out doing this also works, and this is a little bit simpler. But it's more complicated to see why that works. Okay, yeah?
Are all three of those values equally likely?
Yeah, so if you make them equally likely, that works. You can also make the 0, so the 0 is 2/3 of the time, and that'd be even faster. If you make it more than 2/3, there's a special cutoff at 2/3. If you make it more than 2/3, then it starts to break down for certain reasons.
So you just want your -1 and +1 to be equally likely?
Yeah, and then the -1 +1 are 1/6 of the time each, yeah. So you can do that as well. There are a few kind of other ways you can kind of speed this up. There are ways you can. So this turns out to be some. You can write all these -1 +1s as a matrix, and this you want to say how sparse can you make this matrix. This one says that 2/3 of the entries can be 0. There's a way if you do it very carefully, you can make even more of them 0, but it gets more complicated, and I wasn't planning to cover that. But if you're interested, you can come talk to me, and I can point you towards some of that stuff. Okay. All right. So this was all I wanted to say on these approach with on doing these random projections. Any questions on this? Okay. So it's a really cool technique. The theory is very cool behind it. In practice, you really need really large dimensions for it to be useful. But at that point, it does start to become useful in some of these settings. Okay, so we're going to kind of move on to the second kind of topic we wanted to talk about. And so this is the compressed the compressed sensing problem. Okay, and so this is kind of, so we're going to switch a little bit here. And so now we're going to kind of, this assumes, so it's going to kind of assume that there's some underlying model where our unknown data, in this case, is going to be some, is going to be a signal S, and we're going to say that the length of S is going to be D, but it's going to have it's going to be all zeros except for m entries. Okay, and we're going to assume that m is much less than d. Okay, so an example of this. So often we'll treat S as a vector. So in this case, we'll say that S transpose would look something like 0, 0, 0, 0, 1, 0, 0, 0, 1. It's going to look something like this. Okay, so it's mainly zeros except for a few ones. Okay, and then in general, sometimes you can look at cases where these aren't just ones, but there's some interesting value. And sometimes these zeros are not exactly zeros. Sometimes they have a very small amount of noise. But the noise they could be like 0.0001, and there's some measurement noise, and all of the true values are much greater than 1. So there's some real true signal, and then there's some maybe very low noise. But for this class, to just kind of give how this works, we're going to treat it as just being zeros and ones. Okay, and it's almost all zeros. And so the examples I give, they're going to be small enough I can write them on here, but we're going to think of this as actually being much larger. And so, this has 4 ones and probably like 12 or 16 entries. But in general, it'd be like less than 1% of the objects are ones. And so I can't draw less than 1% unless I draw unless I draw 100 zeros, and that's going to be kind of too big here. You can work it with smaller regimes than this. In this setting, it's still interesting, but yeah. Okay. So now, but this data is going to be unknown. Okay. So what we're going to be actually given, so we're going to treat this like the model. So this is going to correspond to the model that we're trying to learn here. So instead of a linear model, it's this sparse model. So what we're actually given as the input is 2 things. So one is the measurement matrix, which is going to be X. And this X is going to be D by K. I think I have this. So D by K, yeah. D by N. Okay, I would just get my notation so it aligns with the notes. This is going to be D by N. And then you're going to have some observations, Y, which is going to be an n-dimensional vector. Okay, and so the idea is that you somehow got Y by doing X times S transpose. So you somehow had this value S, you measured it with some matrix X, and you know what X is, and you got these values Y, and now you want to try and recover S. Okay, so if Y is smaller, if N is smaller than D, then in principle you really shouldn't be able to do this, right? There's not enough observations for you to actually figure out all of the best values here, right? If we're doing kind of this least squares approach, you need more observations than you have coordinates you're trying to understand. But because we're assuming it's sparse, we're going to assume that M is less than N. So we're going to assume that M is less than N is less than D, and then we can still recover M. Okay, so in particular, what you typically need is that N is equal to some constant K. Let me write this as a C here. Some constant C times M times log of D over M. Okay, so if I were to just store this vector S and I were to store it in a way so I wasn't clever about it, right? If I were to store this, I'm going to need m bits, right? But if d is much less than m, I can do better. I can just store the location of each of these. If m is much less than d, I can just store the location of the m items. And it's going to take me basically log d to tell me this location. To tell me the location of this item, it takes log of d to tell me this location. And in fact, you can actually do some clever encoding where you just store the difference from the last one, and then it takes log of d over m to store the encoding. So this is basically the size of the encoding of S. And there's some extra constant here in addition. And the constant C, I think, typically needs to be between 6 and 20, depends on the algorithm you use. So there's some things that, like, if you have an extra 6 measurements, there's a way to recover this up to the length of the encoding, which is pretty cool. Okay, so all I'm getting are these measurements, these observations from this measurement matrix, and I want to recover this vector. Okay, so let me so go through an example shortly to kind of see how this works. But let me try and talk about some kind of applications of this. These applications are not going to kind of, you're going to have to think, we have to kind of abstract out this idea of this signal being sparse. Okay, so often what they do, so this was actually, a lot of this original work was developed inside of computer science, machine learning, but actually inside of the signal processing world. And so they think about this as kind of like if you do like a discrete, like a discrete Fourier transform, then of some sine waves, then you're going to get a couple of discrete values describing the signal. And so they're thinking of this as kind of describing of some mapping through something like a Fourier transform, discrete Fourier transform, into something where it looks like a signal that's discrete. But a couple of applications where people have used this to try and give you a sense of how to generalize this idea. One way was called a single pixel was called a single pixel camera. Okay, so the idea is that if you're taking a picture, so how many people have taken a picture and saved the picture in RAW format? Okay, a few of you actually know what this means. How many people know what RAW format is? Okay, so RAW format is when you take a picture with your camera and you store. We talked about this earlier. You store all of these values of the individual pixels, essentially. You're storing all this information and some other meta information in there. But for most cameras, you take this picture, and what's saved inside the camera before it gets outside the memory is it's transformed into like a JPEG. This is a compressed format. And so people do this because most people who are not kind of doing all sorts of manipulation with the photos or care all that much, they're just taking pictures of their cat or something, the JPEG format is just fine. It's capturing everything that's going on. There's some compressed view of this picture which is kind of capturing most of the information, and they compress it to a JPEG because it takes a lot less space. So you can take a lot more pictures instead of saving all of the individual pixels. Okay? And so the idea is that there's some model where there's an underlying sparse representation of this. If there's some compressed way of saving it that has basically the same picture, then there should be some simpler way of describing it, of what's going on there. And so what people have done is they've figured out with this single pixel camera where they have so this matrix X, essentially each column of this matrix is kind of one measurement of the entire, each row of the matrix is a measurement of the entire data set, but it gives you just a single value, a single pixel. And then you repeat this with a bunch of these rows, one at a time, and you're always getting a single value at a time. So if you look at your camera, it's got this sensor, and it's for every pixel in your image, it essentially has a single sensor that captures the light correspond to that pixel. But they say, well, we only need one pixel, but we need to use it multiple times, where we kind of take a kind of a linear combination of all the measurements together. And so there's people built this single pixel camera where they just use one sensor and with these random masks, and we'll see how to construct this matrix. And it could reconstruct these images. It turns out it didn't work all that well, but it can kind of work okay. You can kind of see what's going on there. It was kind of like a proof of concept. So this was kind of probably a little bit overkill in what they kind of were trying to do. This wasn't a very. The problem is it's not a very underlying sparse solution. I looked up like the difference between raw and a standard JPEG encoding is like you're going down like 20%, right? So if you're only saving 20% here, this is not really worth it. If you're saving like going down to 1%, then this might be a lot more worth it. But saying that the signal is not actually that sparse, so that was kind of the problem here. Where this is used, and I've heard this. I haven't read papers, but like in the spelled that completely wrong. So in this Hubble telescope. So who knows what the Hubble Telescope is? It's this kind of satellite that has a huge camera on it taking pictures of space, and space is like the definition of sparse, right? So they call it space, right? So there's very few locations where there are actual stars. And so it's kind of like this, where most of the pixels are just black, right? If you look out there, even if you kind of really look in deep, it's mainly black. So you only have to send back where there's actually information. And the thing is, the amount of one of the main bottlenecks is communicating between Earth and this telescope. That's very expensive. So they want to compress these images when they're sending them down, so they can use this compressed sensing in order to do that. I'm not sure they're actually. I've heard they try doing this at least. One place where this is definitely used is doing like an MRI on kids. So an MRI is this other way of taking images of people, trying to kind of figure out what's going on inside your body in various ways. And the problem is, kids, they can't sit still. Right, so if you're in one of these MRIs, you have to sit there for maybe it's like 20 minutes, because it needs to take lots of different readings from different angles. But kids have trouble sitting there for 20 minutes. So maybe if you want a really high resolution, you have to sit an hour. So what they do is they take these random measurements, many of them at once, and then they try and kind of reconstruct it afterwards. And so they actually use this for these MRIs on kids. They take like a fraction of the time, and they get near the best resolution. It's not quite as good resolution as before. It's missing out on some of the very small amount of noise. But it actually, this is what they use for doing MRI on kids. And so kind of in general, the principle is that if you have noisy data, if you think of these not as zeros but as being very small noise, in certain cases you think there's these really important coordinates here, and I want to isolate these, and anything that's noise, well, I don't really care about reconstructing this perfectly. I just want to zero this out anyway. So I want to pretend that this was zero. So when we were doing PCA or SVD, we were doing this. We were setting some of the singular values to 0 to get the best rank K approximation. That's kind of doing. You can kind of do a similar thing here, where you find the best kind of reconstruction with only, say, I have a budget of only M. Maybe in this case it's 4 things I want to measure something, coordinates I want to measure with. Let me find the best fit with only 4 of these dimensions. Okay, so that's what you're trying to do here. Okay. Okay, so it's a really kind of cool area that you can actually do this. So let's go and describe how this actually works. It turns out for this measurement matrix, you're going to make these, again, is going to be random from -1, 0, and +1. +1 here. So this can be a matrix filled with random -1, 0s, and +1s. Okay, and what that's kind of going to mean is that for any one of these signals that comes through, on any one of the things you multiply it by, it's equally likely to be a -1 or +1, so it's going to kind of cancel out on average. And except when it doesn't cancel out. And so the times when it doesn't cancel out, you want to say, something didn't cancel out there, and then you can find it. Okay, so it's kind of what's going to happen. All right, so let's go through. Let me write down an actual example, then I'll describe you orthogonal matching pursuit, and then we'll actually work through this example. Okay, so this will be, so my signal, which we're not going to know, and so I've got a different example in the notes than what I'll do here, so you'll be able to see this again. Okay, so this is my signal. So in this case, D was equal to 7, and M is equal to 3. And then my measurement matrix, X, is going to be, and so I kind of created this at random, and this one turned out to work pretty well. The one I created another random one in the notes, and that one did not quite work as well. You'll kind of see. And I mean, it just didn't work as well with the orthogonal matching pursuit algorithm. That one kind of needs a lot of extra measurements to guarantee it's going to work. And I wanted to make the example small enough that you could actually pay attention to what's going on. Okay, need 0. I did 5 rows here. Okay, so this is my measurement matrix X. And so if you see the number of rows here is n. This is the number of measurements I'm going to be doing here, whereas the signal has dimension d. So d lies along here. Okay, and so now if I do this measurement, this is going to be x times s. It's s. Oh no, this is s transpose. Wait. No, this is just s here. Okay. This is x times s. Then the output here for y is going to be -1, -1, 0, 1, -2. Okay, so on average, these y's should be 0, right? Because each element was randomly a 0, 1, or -1, and so anything in here is gonna, on average, is gonna map to 0, no matter what its value is. And so I get some negative ones, some positive ones. It turns out I have a little bit more negative than positive. That happens. Okay, so it's good to keep in mind that only this part is the input. The value s here is unknown. This is the input here. And so this here is unknown. And I want to try and recover this vector s. Okay? Okay, so how am I going to do this? We'll talk about an algorithm called orthogonal matching pursuit. And so this is basically just a greedy algorithm for doing this. I'm going to try and find, so basically the idea is going to be matching. It's going to find the single value, potential value of S, the single dimension, which best explains this relationship. right? I know this is how I measured it. I know are my observations. What is the best guess of some value in S that was non-zero that explains this relationship? Okay, so and then I'm going to find that value, and then I'm going to factor that out, and then I'm going to repeat. So you're going to have 3 steps. You can do the best guess. Then I'm going to factor it out, and then repeat. Okay, so let me kind of go a little bit more detail what this means. So the first thing I want to do is I want to find the column xj, which is my best explanation of which column. Now each, so each column here corresponds with one of these entries in S. Each column is going to affect all of the measurements, right? So I'm going to find this value, which is going to be the arg max. So it's going to maximize over all these xj in X, right? So it's going to maximize the dot product of y comma xj, the norm of this dot product. Okay, so that means if I took y and I took the dot product with any column, I want this to be very far away from 0. And if I assume that these are always going to be +1s or 0s, then I don't need the absolute value. I just want it to be large. If it's negative, that's giving me that's going to imply that the value in here would be negative, and I know that's not true. But in general, I just assume that there's something far away from 0. Those are going to be the interesting things. And so then you want to take the absolute value. So if I look at this, in this case, I'm going to set j. So for this example, I'm going to set j equals to 4. So then x4 in this example is going to be 0, -1, -1, 0, -1. So if I take the dot product with y here, this -1 and the -1 is going to be 0. -1 and 0 is going to give me 0. -1 and -1 is going to be 1. -1 and 0 is 0. 0 and 1 is 0. -1 and -2 is 3. So this dot product value here will be 3. Turns out there are going to be some other columns that will give me the same thing, and I'm not going to know which one to pick. Turns out picking 4 turns out to give me the right answer. If you have many more observations, the one that has the maximum value is more likely going to give you the right answer. In this case, there were some arbitrary choices, and I know the answer, so I actually got a little bit lucky. But otherwise, I pick one arbitrarily. So I find the column which maximizes this. Then the second thing is that I'm going to find, and this one, if you know it's 0, 1, then you don't have to do this. You want to find the best weight of this column. So I'm trying to guess what this value is. In this case, I know it's a 1, but in general, I may want to find this value which does arg min of gamma of y minus xj gamma. Okay, so basically I want, if I multiply this column by, say, some value, in this case I'm going to set this equal to 1. In this case it'll be equal to 1. So this, I want to make y, this observation minus this explanation, as small as possible. Right? So that's going to be my goal here. Right? And so in this case I'll set this to 1. And then the third thing is, so that was kind of came in between here. Then I want to factor this out. So then I want to find So I want to find this residual. So R is going to be y minus xj gamma. So this is what's left over. In this case, if I took y and I subtracted out x4, what's left over is going to be minus 1, 0. Now I'm going to subtract out a minus 1 from 0. I'm going to get a new entry, a plus 1. This plus 1 is going to stay here, and this is going to be a minus 1. It's gone from minus 2 to minus 1. And so the norm of this vector should gradually be getting smaller. I'm explaining more of the observation as I do this. Okay? And so then I'm going to repeat this, but instead of repeating it on the original y, so I'm going to repeat this next time. Then I want to repeat on R. So this R is called the residual. Okay, so I want to repeat on this residual. So instead of here, this is now R. So this is the argmax of what's left. What's the best explanation of that? Then I want to, in here, I want to replace this Y with an R. The best weight that says the residual minus this explanation. And then again, I'm going to subtract from the residual to get a new residual. And I kind of want to keep doing this until the residual either it completely disappears or I can't do any better. Right? So this is the orthogonal matching pursuit algorithm. So it's pretty simple. You kind of find one explanation at a time and you factor that out. So it's called orthogonal because every time you do this, your explanation is orthogonal. It's a completely different explanation than everything that came before. Okay, so the matching pursuit, well, the pursuit, I think, is you're kind of pursuing the answer. The matching, I'm not sure what that means. But but it's a pretty simple algorithm. You can use this for things other than just doing compressed sensing. Often you have a lot of data. You're trying to find the kind of the variables which best explain what's going on. People will actually use this. There are a couple of potential issues with this algorithm. It can get stuck in local minimum. So it won't always converge to the right answer. It turns out in the compressed sensing problem, if you have like 20 more observations than you actually have non-zeros, then this is supposed to work with high probability. But in general, it's not going to always give you the best answer. It can get stuck. If you make the first choice wrong, you're going to kind of get in trouble. Okay? So sometimes what you do to fix that is instead of solving for a single weight here, so say you can say, well, I know I've already committed to saying that at x4, I already chose this value to be something. So then, say in the next time through, turns out the next time through, you may choose x3, so that you may choose this column the next time through. So then if I'm in this step, instead of solving for just the weights on the third column, I can solve for the weights on both the columns together. So this is just, if I want to minimize this, I can make this, say, a least squares minimization. And then I can solve for this exactly using just the least squares solution. Right? So this is the same problem here now as this subproblem is now the linear regression problem. And because I've chosen only a small number of variables, I have fewer variables than I have observations, and I can solve this. Okay? Sometimes you also want to add, instead of minimizing this, you want to add some extra term that is actually regularizing this. So I'm going to add some penalty, so some constant times the norm of gamma. So I want to penalize for having large values inside of here. this will also tend to give me a sparser solution. And we'll talk. We previewed this in the first lecture on regression. We did the overview. Said this will give you a biased solution to the least squares, but that bias is towards often a sparser solution, especially if you make this the one norm here, where this was the 2 norm. So if you bias towards a sparser solution, then this will also help. And so if you do these 2 add-ons, then this will converge even a little bit better. It's harder to kind of work through these examples, though. But if you were to implement this, then you can add this add-on instead. And so in class on Wednesday, we'll actually see why adding on this regularization term will bias towards sparsity. And so the more advanced ways of doing the compressed sensing, instead of using orthogonal matching pursuit, will then instead we'll use this form and actually solve for all the variables at once. Okay, and sometimes what you do as well is that you will choose a value j that you think was a good explanation, and then later you'll say, well, it turns out I get a better explanation if I set this to 0. So then you throw it away again. So if you allow yourself to resolve for these old values, then you can sometimes get out of these local minimum you would get stuck in otherwise. So, all right. So it's kind of a and then there are a variety of other things that you can do to try and solve this a little bit better. But this is the starting point for most of doing stuff in compressed sensing. And this is a pretty easy algorithm to implement, even with these add-ons. Remember, if this was an L2, it was a 2 norm here, then you can solve this in a closed form the same way you're just solving the least squares. So then this would be called then doing this would be called doing ridge regression instead of least squares regression, so that'll give you like a pretty good solution. Okay. So let's. Any questions on the algorithm? I figured I would go through the rest of this example here to kind of see how it works. Or do people questions on the structure of it? Okay, so let's go through the example. So after we did this residual, after we factored out column 4, what was left was -1, 0, 1, 1, -1. Okay, so then if we go back through this step again, we'll write this step in red, then the solution here is going to be j equals 3 is going to give a good solution because the dot product of this with the third column, -1, -1 will give us +1, 0, 0, 0, 1 is going to give us 0, a 1 and a 1 is going to give us a +1, and this is 0. So we're going to get a +2 here. Turns out all the other columns are either going to get the same value or everything is going to cancel out. Like if I looked at this second column, -1 and 1 gave me a -1, 0, 0, 0, 0, 0, 0. And then this is another -1, 1. This also gave me a -2. So it's the same norm, but this was negative. If we looked at the first column, so the 0, get a 0 here. This is a -1, a 0, another, also a norm 2. Okay, this is a 0, a 0. This is a -1, a 0, and a +1, and these cancel out. So the norm of the fourth column is now 0. We factored out as good as we could, and that's because we chose the best explanation. But on average, when you get more data, most of the stuff is going to cancel out. And so you'll get one column that's smaller observation. Okay, so now we'll assume that we'll set the value to 1, and we'll subtract out to get a residual. We'll call this the residual after step 2, and it'll be this minus column 3, which times 1. So this value minus the third column. We're going to get a 0, and then we subtract out a 0 from 0. Subtract out 1 minus, so then 1 minus 0 is going to be 1. 1 minus a 1 is going to be a 0. and a -1 minus a 0 give me a -1. Okay, so now after the second round, this residual has gotten smaller, right? I started here, and this one had a norm. Just if I added up all these entries, I got 1, 2, 3, and 5. Maybe you square this, you know. But this came from 5 things down to 4 things, and now I have 2 things left to explain. And now if I looked at the best value the third time around, I'm going to get j equals 7. Turns out, if I look at the 7th column here, then it's going to be 0, 0, 1, 0, -1. It gives me a norm of 2 again. It matches it perfectly. If I used anything else, I couldn't get any more than that. So J7, and then if I subtract out here, it's going to be all zeros. I'm going to get a perfect explanation. And it turns out that's because I chose the 3 entries where I had 1s. So it worked out. Right? If you choose something wrong, you won't get a great explanation, but it will always steadily decrease at a pretty good rate. And if you know after a certain number of steps, either you'll get stuck or you'll have achieved a certain amount of reduction in the norm. So you get a pretty good explanation. So even if it gets stuck, every time you're making progress will be pretty good. Okay, so any questions on how this worked? All right, so the homework 5, I've unofficially posted homework 5 if you want to look at it. The bonus question is going to ask you to implement this, and I think I set it up so that the only way you can do it, there's no arbitrary choices here. That the only way to solve always the maximum, the best choice of column it'll actually recover it. So you can actually try it with just the basic algorithm for the orthogonal matching pursuit. Okay, so the class on Wednesday we'll talk about how to do the lasso, which is going to be this way of doing regression that's going to bias, and it's also going to, one of the things that's going to bias towards is a sparse solution, and we'll explain why it biases towards a sparse solution. And it's going to be more complicated to solve than least squares, so we'll talk about how you actually solve for the lasso solution. You can still do it, which is kind of maybe a little bit surprising once you see it, but okay, great.